Hello and welcome to my channel. Myself Abro, and today I'm going to start with a very good topic named transformer, part of the electrical machines. So I will just give you what is a transformer. Transformer is nothing but a static electrical device which means converts the voltage. It steps up the voltage and steps down the voltage. In a thermal power plant, it steps up the voltage for efficient transmission, efficient HVAC transmission, or the HVDC, mainly the HVAC transmissions. So now I'll just give some of the formulas as well as the equations, and then we'll go forward with the numericals, which is very much essential for the students who are studying electrical engineering in their bachelor degree. Even they are studying in energy engineering or energy management in their bachelors and masters. Even very much helpful for mechanical students too. So now I'll start the transformers along with what is the equation of the transformer. So I will start with the topic named transformer. Transformer is a static device. So there are two types. One is the step up transformer and other is step down transformer. Step up transformer and other is step down transformer. So there are the turns named N1 and phi is the flask. Step 1 transformer, there are two turns, mainly N1 and N2. N1 and N2 are the two turns in the transformer. N1 is the primary turn, N2 is the secondary turn. In step up transformer, N2 will be greater than N1. So the voltage, secondary voltage will be also greater than primary voltage, and primary current will be also greater than this primary current. Secondary current will also be greater than the primary current. And step down transformer, that is totally opposite. The step down transformer, the N1 will be the number of primary turns will be greater than the number of secondary turns. The primary voltage will be greater than the secondary voltage, and the primary current will be also greater than secondary current. So main equations, as we know, that is E, that is the EMF equation, is equal to minus N d phi by dt. Phi is the flask which we differentiate with respect to time. So we know that the phi is equal to, we can also write phi m sin omega t. We can write this. This is nothing but the EMF equation. This is the EMF equation of the transformer. So we can put phi over here, that is E is equal to minus N d by dt of phi m sin omega t. So we can now differentiate with this one. So omega will come above. So minus N omega. Then if we differentiate, divide by dt, that will be cos omega t. So we know that omega, as well as from the physics equation, omega is equal to 2 pi into f, 2 pi into frequency. We can directly write minus n, that is omega, we can write into 2 pi into f into cos omega t. I hope I'm going in the right directions. Your understanding is equal to minus n d phi by dt. Phi is equal to phi m sin omega t. We are putting the phi omega as a 2 pi f. So, and we are first differentiating minus n omega cos omega t. Then we are coming into this minus n into 2 pi f. So if we just calculate directly, that it will come, that is minus n, that is 2 pi f. So we are just converting cos, that is cos omega t, that is omega t minus 90 degree, or no, I'm sorry, this is not cos, it will be sin omega t minus 90 degrees. So minus will be cancelled. So just it is an EMF equations, and if we go to the RMS value you can direct remember the equations. That is always that is E by root 2. If we just divided by root 2, that is 4.44, then phi f into n. So this is so for E1 it will be phi 1 f1 n1, for E2 it will be just 4.4452 F2 and N2. So this is the EMF equation. I will check what is the direct value which is coming over here. That is 2 pi Fn into 5. This will become at a 2 pi Fn into 5. So this will come after here, minus will be cancelled. We are putting cos omega t minus sin omega t minus 90 degree, minus will be cancelled, 2 pi Fn into 5. So this is the equation. We are dividing by root 2 to get the RMS value. You can directly memorize the equation, which is very much essential for the numericals. That is 4.445 F into N. So I hope this is clear. Now I'll go into the next part of the transformer. That is what are the losses in the transformer. So I hope this part is very much easy for you. What is the step up, step down transformer, as well as the EMF equations in the transformer. Now I will go what are the losses in the transformer. So losses in the transformer, there are mainly coal loss, and other is copper loss. Copper loss also we can tell, that is called I square R loss. So now I will tell that what is the transformer efficiency. Transformer efficiency, we know everywhere what is called efficiency. Efficiency is nothing but output by input. So, and you know what is the input. So when in a system, this we are giving, this is a system, here the input is coming, and there is output, and there is always the losses. Losses takes place in the electrical machines. There is always losses takes place. So we can write output in this input is equal to output plus losses. Output plus losses. Output plus losses. So, so what are the type of losses where we can consider as the copper loss as well as the coal loss? That is coal loss, copper loss. Copper loss is I square R loss. So now we can tell what is the output. Output of an electrical machines. Output is equal to P is equal to V2 I2 cos phi 2. V2 I2 cos phi 2, and losses we can keep the losses as iron loss. We can write as Pi. And plus what are the losses, that is other is the copper loss. Copper loss we can write I2 square R2 we can write. So now we can go directly to the equation. Efficiency is equal to output but nothing but V2 I2 cos phi 2, that we will divided by input is equal to output plus losses. We'll just write the same equations, V2 I2 cos phi 2 plus Pi is nothing but the iron loss, and this is the copper loss, I2 square R2. So now we'll just take, this is the numerator, this is the denominator. We will just differentiate the denominator with respect to current, means d by di. So now we'll put this equation d by di, and we'll differentiate into V2 I2 cos phi 2 plus, this is the losses, that is the iron loss, plus copper loss I2 square R2, and that will equate with 0. So now if we differentiate this with respect to I, this will turn into 0, and this we will differentiate, and this. So now you can write a 0 plus, if we differentiate this one, this will be I square, that is if we just differentiate this, what will be the answer? So if we just differentiate d by di into R2, so it will be just, it will come around, it will come down, and it will be, I'll write this one, that is a Pi will write as usual, and this will differentiate into I2 d by di, that is plus, this will be plus, this will be minus, and this will be I square minus I square, this will come out. I'll just check the equation. So what is coming over here, that is P by I square, this is P by I square, it will come down, and this is minus Pi is coming over here, current, and this is the P into I, and that is coming here 0 P into plus R2. So if we equate into 0, now just R2 we can write here directly P divided by I2 square. And now if we just equate this equation over here, therefore R2 into I2 square is equal to P. So Pi is nothing but this is the iron loss and this is the copper loss. So iron loss and copper loss, and so this is the so these are equal. So efficiency is maximum. Efficiency is maximum when the iron loss is equal to copper loss. So I hope this is now easy to you how it has come. Efficiency is nothing but output by input. Input is nothing but output plus losses. So this is the output power, that is V2I2 cos phi 2. So we are just taking V2I2 cos phi 2 divided by V2I2 cos phi 2 plus iron loss plus copper loss. We are differentiating the current in the denominator part. So just it is coming, it is going to be 0 plus Pi plus Pi. This is coming as P by I2 square plus R2. R2 will remain as equal to 0. We are just equating this as is equal to R2 into I2 square into Pi. So this is nothing but the copper loss and this is the iron loss. So now it is the efficiency. So when we are getting the maximum efficiency when iron loss is equal to copper loss. So I hope this is clear to you. Now I will erase this part. So I'll directly jump into the numerical part. So this I'll go to the first questions, that is a low voltage outdoor lighting system. A low voltage outdoor lighting system a low voltage output lighting system uses a transformer that uses a transformer that steps down that steps down 120 volt to, it steps down the voltage 120 volt to 25 volt. Now the equivalent resistance of the low voltage lamp, the equivalent resistance of low voltage lamp is 10 ohm. So they are asking what is the current in the secondary coil. What is the current in the secondary coil? So I hope you have understood what is the question here. A low voltage outdoor lighting system that uses the transformer that steps down the voltage 120 volt to 25 volt. The equivalent resistance of the low voltage lamp is 10 ohm. So what is the current in the secondary coil? So you know, just these are transformer. We have to take the data. First of all, when the numericals are given, we have to take down which is the data here. So there is a transformer equation, that is the V2I2 is equal to V1 into I1. V1 into I1. So this is the normal these equations. So first of all, to get down the equations, we have to take the data, that is what is the step down voltage 120 volt, that is V1. V1 is nothing but 120 volt, and what is the V2 here? V2 is 25 volt. So now we have to take the we got the data from the equations V1 and V2, and other is there, that is the I2 is also given, that is a voltage in the low voltage lamp, that is this is the resistance R, that is given 10 ohm. So it is very easy numericals, just if you know the formula and given data, you can just directly calculate these equations. That is, here is the I2, from these equations I1 is equal to V2 into I2, V2 I2 divided by V1. So here we just put the values. V2 is nothing but 25 volt into so here is another the current we have to get here. Current nothing but I2 is equal to V2 by R. So here is a V2 25 volt, 25 divided by resistance is 10, so we are getting 2.5. so here we can just add 2.5, therefore V1, what is the V1? 120 volt, and if we just multiply, that is 62.5 divided by 120. If we just divide 62.5 divided by 120, the answer will be around 0.5 ampere. It is 0. It is very much easy questions, these numericals which came, and also it is also for important for semester as well as competition exams. So this is this one equations numericals. We have got the current in the secondary coil. We are getting, that is primary coil is a 2.5 ampere. So, and this is the primary current, and this is the secondary current. I hope this was easy for you. Now I will go towards the next question. Next question will be mainly based on the efficiency calculation for the transformer. That is also very easy, that what is the output and what is the input. So if we know what is output and input, we can easily calculate the efficiency of a transformer. So next question is, in a 50 volt ampere transformer, 50 volt ampere, it is given as kilovolt transformer, kilovolt ampere transformer. The iron loss is 500 watt. The iron loss is 500 watt. What are the next part of the question? And full load copper loss, and the full load copper loss is 800 watt. Now other part is the efficiency of the transformer at full load. What is the efficiency? What is the efficiency of transformer? What is the efficiency of transformer? What is the efficiency of transformer at 0.8 lagging, 0.8 power factor lagging? So we go to the power angle of the transformer. We just know this is the kilowatt. This is kilowatt. This is nothing but the active power. This is active power, and this is the reactive power, that is kVAR. This is nothing but the reactive power, and this is the apparent power. Apparent power is kVA. Apparent power. This is apparent power. And this is the angle, that is the cos phi. So cos phi, we can directly write what is the cos phi. Cos phi is equal to kW by kVA. So this is also very much important equations. Cos phi, power factor, is equal to active power by apparent power. This is very much important for semester as well as the competitions for electrical engineering and energy management point of view. So this we know that kVA into cos phi. So nothing, just we'll write kilowatt is equal to kVA into cos phi. So now we just put the equations. What is given 50 kVA? We just put 50 into 0.8. So it is 40 kilowatt. So now I think you have understood how to calculate. So this is the power. That is the power. That is nothing but the output power. So it's the output by efficiency. This is the output power. So output power. Now we calculate the what is the input. So input power is nothing but P output plus losses. So what are the losses? Here we know 40 watt plus we have this loss 50 watt, that is the iron loss, 50 watt, and other is copper loss. So we just write we just convert into 0.5, that is in kilowatt, and 0.8. So it is coming 41.3 kilowatt. So now it is very clear to us how to calculate the efficiency. Efficiency is nothing but output by input, and so we just put the values, that is 40 divided by 41.3 kilowatt. So if we just do the calculations, so calculations that is efficiency is nothing but into 100%, it will come around 86 or 87%, I think. Sorry, it's 96 or 97% efficiency calculation. It is just like you need to calculate with the use of calculator, but I hope that how to find out the efficiency of the transformer, it is very clear to you. I can just give a short description. This is the active power, this is the reactive power, and this is the apparent power, and this is the cos phi. Cos phi is nothing but the power factor, that is kilowatt, active power by apparent power. Now we can write kilowatt is equal to kVA into cos phi. Just we put the values, power factor into the kVA of the transformer, that is the output power, that is 40 kilowatt. Now input power, we always know that output plus losses, and that we have calculated with the total losses, that is the iron loss and the copper loss, and that is 41.3 kilowatt. And so we have calculated the efficiency by P out by P in, with output power by input power, and that has come around 97% efficiency if we calculate. So I hope you have understood. Now I'm going towards the small other numericals, which is also very much useful, as also very important for your semester point of view. So I'll go in my next part of the numericals. That is very much important, so need to learn with me. So now I'm going to the next part of the question, that 230 to 460 volt transformer, 230 by 460 volt transformer, 460 volt transformer has a primary resistance, has a primary resistance of 0.2, that is ohm,